Hello. In this video, we will look at computing the impulse response of a linear time invariant continuous time system, or an LTIC system. Our starting point is the representation of our LTIC system by an ordinary differential equation shown over here. We can also write this ordinary differential equation in operator notation. D is the differential operator d by dt. So Q of d is simply going to be a polynomial of degree n, or of order n, that acts on our output signal y of t. P of d is going to be a polynomial of degree m that represents the differential operator acting on our input signal x. And what we're concerned with over here is determining what's referred to as the unit impulse response of the system represented by this differential equation, or sometimes simply referred to as the impulse response. The impulse response is defined to be the output y of t when we apply as our input signal x of t the impulse function delta of t, and we use zero initial conditions. We denote the specific output as the impulse response h of t. The impulse function, our input, appears momentarily only at time t equal to 0 and then is gone forever. But at the moment that it appears, it actually generates and creates energy inside of the system. This energy is associated with non-zero initial conditions that appear instantaneously, and it is these non-zero initial conditions that are then responsible for producing our output signal, or effectively determining what is referred to as the impulse response h of t. Now, the impulse response is important because for an LTIC system, if we know the response to a unit impulse delta of t, so we know h of t, then in theory we can determine the response of the system, or the output of the system, for any arbitrary input signal x of t. To obtain the impulse response, we have to solve the following ordinary differential equation. We recognize that this differential equation stems from the original differential equation representing our LTIC system. The only thing is we've applied as our input signal the impulse function delta of t, and so the output of the system we simply denote then as our impulse response h of t. Now, for time t positive, the impulse function is equal to 0 because the impulse function is only defined at time t equal to 0. As such, our differential operator q acting on h is going to identically be equal to 0. This tells us then that h of t must be a sum of characteristic modes. Moreover, h may contain an impulse function at time t equal to 0 if m is equal to n, or if the order of the differential operator, the polynomial differential operator acting on our input signal, is the same as the order of the polynomial differential operator acting on our output signal y of t. So the general form for impulse response is going to be given by an impulse function plus a linear combination of our characteristic modes multiplied by the unit step function. Just to remind you, B0, the coefficient of the impulse function appearing in the impulse response, is in fact the coefficient of the leading order term acting on the leading order term of the differential operator acting on our input signal x. So in order to determine the full impulse response, we need to determine the remaining coefficients over here, which is to say what specific combination of the characteristic modes do we have for our impulse function. To determine the specific coefficients over here, what we simply have to do is to substitute this form for our impulse response back in this differential equation, apply the differential operator to it, apply the differential operator p to our impulse function, and then equate like terms on both sides of the equation. This is referred to as the impulse matching method. An alternate way to obtain the impulse response is to use what is referred to as the simplified impulse matching method. And using the simplified impulse matching method, the impulse response is simply given by B0 delta of t plus P of d acting on y sub n of t multiplied by the unit step response. So again, B0 delta of t, or the coefficient B0, is the same term over here, and delta of t appears only if the order of the differential operator, the leading differential operator acting on our input signal, is the same as the order of the leading differential operator acting on our output signal. P of d, if you recall, is going to be the differential operator that acts on our input signal. So remember, this differential equation representing our system could be given an operator notation as q of d y of t is equal to p of d x of t. So we take this differential operator p of d and act on y sub n of t. Y sub n of t is again a linear combination of the characteristic modes of the system. To determine the specific combination of these characteristic modes, we subject y sub n of t to the following initial conditions. So once we find the appropriate linear combination of our characteristic modes, we have y sub n of t. We then use our differential operator p of d act on y of n. We multiply this by the unit step function, and we add, if necessary, this impulse function, and this gives us our impulse response. If you have any questions, send me an email.